Today we're talking about reactions, and not recognizing chemical reactions, not identifying the types of chemical reactions, not even balancing chemical reactions. All those skills are really important, but today we want to talk about the nitty-gritty, or how reactions actually happen. And because we can't see that, we're going to need to use a theory, the kinetic molecular theory from, I'm going to call it KMT. So the basic things of the kinetic molecular theory, KMT, that you need to know, and probably something you probably already do know, is that all matter is made of particles. That's probably something you've known for a while. Particles are in constant random motion, and that random motion is going to be kind of important. So is the constant part of it as well. The amount of motion, or how far they can travel in a given amount of time, is dependent upon partly the state. So for example, if I look at solids, they're packed into often a very rigid crystal shape. Liquids have a bit more room to move around. They're still kind of packed together, but they can slide past one another a little bit, whereas gases have no interaction whatsoever with one another. They are free to move in large distances. The other thing is that temperature is related to the average speed of the particles. So again, going back to the motion, if I have a different state, I have a different amount of motion. If I have a different temperature, I have a different amount of motion. Now solids are still going to be locked into that particular shape, or that particular structure, but as they heat up, they're going to move faster. They're going to vibrate back and forth more quickly. Okay, how does that have to do anything with reactions? Well, if I take a look at a simple reaction, you would identify this as an addition reaction, or a synthesis reaction. You would say that that is indeed balanced. But if I take a look at them at the particle level, so a molecule of hydrogen and a molecule of iodine, if I react those together and look at the products, I've got two particles of hydrogen iodide. And if I look at it in more of almost a Lewis kind of structure, then it looks something like that. But if I take a look at the reaction in a little bit more detail, that reaction is going to require bonds to break. So I had bonds between hydrogen and I had bonds between iodine, and both of those had to break apart and form atoms of, rather than molecules of, hydrogen and iodine. And then what had to happen was I had new bonds form. So a new bond between a hydrogen atom and an iodine atom to form that final compound of hydrogen iodide. And if I take a look at that every reaction is going to be some version of that. I mean, whether it's all those bonds breaking and all those bonds forming, there's always going to be something that has to come apart and something that has to go together. Okay, well, how do the bonds break? It's easy enough to say that they do, but how does it happen? Obviously, those hydrogen molecules or those iodine molecules were bonded together for a reason, and they kind of, I don't want to use the word liked it that way, but they kind of liked it that way. They were perfectly fine in that bonded form. So let's look at what a bond is. And we're going to specifically talk about covalent bonds, because in most cases that's what we're going to be dealing with in terms of breaking bonds and forming bonds. So the bond is going to be where one atom attracts the electrons of another atom, and that atom attracted the electrons of the first atom. So in other words, I've got an atom with its electrons and another atom with its electrons, and they end up sharing those electrons. But in order to share those electrons, both atoms have to be attracting to those shared electrons, so that they are holding on to each other. That's what sharing the electrons means. In order to break that bond, I'm going to have to overcome that mutual attractive force between the atoms and the valence electrons. Not the atom and its own valence electrons necessarily. I mean, sometimes it does. If I break a bond apart and it comes off as ions, then yeah, one atom got all the electrons, or at least both of the electrons. But the important thing to remember is that energy is going to be required in order to break a bond. There was something they were held together. I have to overcome that hold together part. So energy is always going to be required in order to break bonds. The opposite is also true. We're not going to go into the hows and whys and examples of it, but the opposite is true, that if two things are attracted to each other, like an atom and somebody else's electrons, if they're attracted to each other and that they are allowed to come together, then energy will be released. So bonds are formed, energy gets released. When bonds are broken, energy is required. And those two things are going to be pretty important. Okay, well, where did I get the energy? If I had those hydrogen molecules floating around, happy as can be, and no bonds are breaking, now all of a sudden the bonds broke. How did it happen? So I'm going to go back to something from the KMT, where particles are in constant random motion. And because the motion is random, and constant, there's going to be a whole lot of collisions. Collisions are happening in the air, for example, all around us, in the water molecules in the glass of water that you have, or whatever. Collisions are always happening. And those collisions do not always result in reactions, but sometimes they do. So what it comes down to, actually I take that back, one more thing, is energy can't be created or destroyed, it can only change forms, and that's something you've known before as well. So if I take a particle that's in motion, that has a certain amount of kinetic energy. I can also turn that energy into a storage energy, which is potential energy, and I can move back and forth between those two. Okay, so here's where I thought I was going a second ago. If I have particles colliding and those particles collide with enough energy, then I can break the bond. Remember, bonds require energy to break. Where does energy come from? It comes from the collision. So the collision, think about dropping a basketball or dribbling a basketball, that's what it's called. I'm going to go do some sports later. You throw the basketball down, it speeds up, speeds up, speeds up by gravity, hits the floor, slows down, slows down, slows down, stops, bounces back. You have that motion energy turned into stored energy, and the energy is stored and used to propel the ball back up into the air. That's about all I know about basketball. So the energy comes from the collision. Okay, let's look at that previous reaction again. My hydrogen, my iodine. I can collide them in a whole lot of different ways, but we're going to look at two. I'm going to look at this one where they're coming in and colliding head on, and when they're colliding in side to side. Now, one of those is going to not result in a reaction because the orientation didn't work out. The other one would. Now, again, I want to stress that I can't see this happening, so this is definitely very theoretical, but it should make sense because if I take those atoms and I collide them together in this form, side by side, then as they collide, then I can start to break the bonds between hydrogen, and I can start to form the bonds between, break the bonds between hydrogen and break the bonds between iodine, and then start to form new bonds between hydrogen and iodine. Now I know I'm kind of going back on something I said before where I said the bonds are broken and then the bonds are formed almost in step one, step two, and that can probably happen, but it can also happen like this where the bonds are broken as new bonds are formed, or the other way around I suppose, new bonds are formed as old bonds are broken. But the bottom line is I need to have these things lined up for that to happen. There has to be a correct orientation. Orientation is tricky because particles are in constant random motion. So collisions are easy. Orientation, that's just a bit of a gamble. Okay, where are we so far? Quick summary. I know that particles are going to collide, lots. I know that if they have enough energy and they have the right orientation, then I can get that whole reaction ball rolling of broken bonds, new bonds need to be formed, energy goes in to break the bonds, energy comes out when the bonds are formed. Okay, that's also what I just said. Bonds are broken, energy is required, bonds are formed, energy is released. Okay, here's the last bit. Anything that can change the collisions or the energy or the orientation is going to change how fast the overall reaction occurs. Fast reactions versus slow reactions. So there's 5 things that are going to be part of our how we can mess with reactions or change the speed of reactions or affect the reaction rate. And they are temperature, concentration, which is true for solutions and gases, surface area, which applies to solids, and then the presence of a catalyst, and finally the nature of a chemical reactant. Now some of those we have some control over, some of those we can manipulate, some of them we can't, but we'll talk about that in class. I do want to spend just a minute talking about catalysts because it's hard to really get a good handle on them once we get into class. A catalyst by definition is a substance that increases the rate of a reaction without being used up. So it's not a reactant, but it changes the speed of the reaction. I want to emphasize a couple of things. That one, it is not energy. So I realize that changing the temperature also speeds up a reaction, but catalyst and temperature are not the same. Temperature represents heat energy, and a catalyst is an actual physical thing. It's a substance. There's different kinds of catalysts, which we'll try and talk a little bit about once we get to class, but for now we want to understand the definition of a catalyst, and that catalysts aren't going to be, they're not magic, they just speed the reaction up. They don't make more stuff. All they do is allow us to make that stuff a little bit more quickly. Whew. Okay, that was a bit of a whirlwind. We'll talk about a lot of these things when we get to class, but in terms of a background, what we're going to do is use those things, the collisions, the energy orientation, try and figure out what's going on with those 5 things that affect the reaction, and then look at some examples of how this actually happens in real life. Anyway, we'll talk to you in class.